In this question, we are given this complex number where t is between 0 to 2 pi. The very first part of this question requires us to take x as the real portion of the complex number z, which means that x is going to be equal to 2 cosine t, and we are going to take y to be the imaginary portion of the complex number z, and y is going to be equal to 3 sine t. And based on this, we're going to try to sketch on an Argand diagram the curve that shows the position of the points that represent this particular complex number z. So if the x coordinates is in terms of t and the y coordinates is in terms of t, what we have here is actually a pair of parametric equation where t is between 0 to 2 pi. So in order for us to sketch the curve that represents this complex number z, where when it is represented in an Argand diagram, this will be the xy coordinates that is on the Argand diagram. Let's try to make use of our calculator to sketch this pair of parametric equation. So I've already sketched on my calculator. I have let x to be equal to this and y to be equal to this. And for the t minimum, I'm going to go for 0, and t maximum, I went for a 2 pi. So the graph looks like this. So it looks a bit like a circle, or rather a circular shape, but if you were to look at it closely, the vertical radius here is 3 and the horizontal radius here is 2. So it might not be a circle, it might be closer to an ellipse, but we are also not exactly sure whether it is an ellipse. But if you were to look at this question actually told us also to find the Cartesian equation of this curve. So I think what I'm going to do is I'm going to delay drawing the curve, and I will take a look at the Cartesian equation first, because if it is really going to be an ellipse, then we do know how to identify the features of the ellipse based on the Cartesian equation. So if I were to work on the Cartesian equation, we are going to make use of trigonometry. I will make cosine t the subject. This is equal to x over 2. And if I were to make sine t the subject, this is going to be equal to y over 3. And if we were to make use of trigo identities, specifically sine square a plus cosine square a is equal to 1, I'm going to write the cosine square first. So cosine square t plus sine square t is equal to 1. So cosine square is going to be x square over 2 square, or 4. Then plus this will be y square over 3 square, or 9. So we do have an ellipse. We have an ellipse with the center at 0, 0. Let me draw a version here. The center is going to be at 0, 0. The vertical radius is going to be 3. And the horizontal radius is going to be 2. And now we are ready to sketch the graph, especially when we know that it is going to go one full round for the ellipse based on the graph that we are seeing on our calculator. So let me do a quick sketch here. This will be the imaginary axis, and here let me go for this as the real axis of our Argand diagram. So it is going to be an ellipse that is shaped that is like this. I'm going to do a sketch. So from here to here, and then to maybe here, come back up again to here. And this is going to be the ellipse, where this is vertical radius is 3, so plus and minus 3 will be here. Then this will be plus and minus 2. So this is going to be representing for us the curve where the positions of points representing the complex number z is. Okay, this is part A of the question. We're going to look at part B of the question. Part B of the question says that there are two complex numbers, z1 and z2, and for them, they are going to be having two distinct values of t such that modulus of z1 is equal to modulus of z2. So z1 and z2, they belong to z. And if we were to be talking about the modulus of z1 to be equal to the modulus of z2 on an Argand diagram, since z1 and z2 can be any point that is here, we are talking about the distance of that point from the origin for z1 to be equal to the distance of another point, another distinct point from the origin. They will be sharing the same distance. So the question wants us to take the argument of z1 to be between 0 to 2 pi. And by referring to the Argand diagram in part A, we want to find the possible values of the argument of Z1 plus Z2. So we are going to be looking at the argument of Z1 to be between 0 to pi over 2. So if I were to use a point to represent Z1, that point has to be lying on this ellipse, on the curve, and it has to be in the first quadrant, so that its argument is going to be between 0 to pi over 2. So I'm going to assume that it may be a point that is here. Okay, and I am going to let this point be, let's say, A. So to do part B of this question, I'm going to let A represent Z1. Okay, so this is going to be A, which means that we know that the distance of this away from the origin is going to be the same as the distance of Z2 from the origin, because that is what the question says. And we want to find the possible values of Z1 plus Z2. First, let's think of all the possible positions for Z2. This is an ellipse, so it is going to be symmetrical about the vertical axis, symmetrical about the horizontal axis, which means that another point that will give me the same distance will be this point being reflected about the y-axis, which means that it can be a point that is here. If it is reflected about the y-axis, it can be a point that is here. So from here to here, they should share the same distance. Let me mark it down. So it will be this. I'm going to call this point here B. Are there any other possible points that will be giving us the same distance as this from the origin, and it is going to be lying on the circumference of this ellipse? Yes, I will reflect this about the horizontal axis. So if I were to be doing that, we will have something that is like this. So from here all the way until here, this is going to be another point. One more point, it is directly reflecting this about the origin. So if I were to be reflecting this about the origin, we will have one more point that is here. In fact, this point is directly below this. It is directly to the left hand side of this. We are actually having a rectangle that is inside this ellipse. So we have all these 4 points here, where A will be representing Z1, then B, I'm going to call this C, D, B, C, D, they all can be representing Z2, because for B, C, D, they are all at distances that are the same as A from the origin. Okay, which means that if I were to be looking at, let's say, this point, for us to be looking at the modulus of Z1 to be equal to the modulus of Z2, and it can be represented by point B. So if it can be represented by point B, and if we were to be taking Z1 plus Z2. Okay, now we are focusing on point A being Z1, representing Z1, and point B representing Z2. So when we take one complex number plus another complex number, we will take reference to 2D vectors. If I were to take it as 2D vectors, it will be this vector plus this vector. And since this angle is the same as this angle, when I take these two vectors, adding them together, it is actually going to be giving me, according to the parallelogram law, a resultant vector that is definitely going to be on the vertical axis. So it is going to be here, this plus this, which is Z1 plus Z2. So if it is going to be a point that is here on the vertical axis, the argument to that point, the argument to the line from that point to the origin, the argument is going to be pi over 2. So from here, we can deduce that the argument of Z1 plus Z2, this is pi over 2. So this is one of the possible values for argument of Z1 plus Z2. And we can analyze the other 2 points also for modulus of Z1 to be equal to Z2. If I were to be representing, actually this is supposed to be for Z2. So Z2 can be represented by point B. In this case, Z2 can also be represented by point C. If I were to be representing it by point C, then Z1 plus Z2, let's think about it. z1 plus z2, if it is vectors, they will cancel out each other. So it will become a 0, which means that for z1 plus z2, we are looking at the argument of 0. And the argument of 0 is going to be equal to 0. In fact, if you were to be looking at point D also, point D is going to be representing z2 such that modulus of z1 is equal to z2. And if I were to take this vector plus this vector, we will be getting a resultant vector that is going to be on the horizontal axis, since these are reflections of each other about the horizontal axis. Okay, so this vector plus this vector, we will be getting a vector that is pointing to a point that is on the horizontal axis, and this will give me also a point that represents z1 plus z2. So it is going to be a point that is on the real axis. The argument of a number that is on the real axis is 0. So we can actually use this to be going for point C or point D. So if z1 can be represented by either point C or point D, the argument is going to be equal to 0. So what are the possible values of the argument of z1 plus z2? It will be either pi over 2 or 0. We can take a look at part C. For part C that we are looking at here, we want to explain if it is necessary for alpha to be real. And to explain about this, we need to at least get an idea of how alpha is related to z1, z2. And I mean, you can either use what you have learned in your secondary school, or you can definitely also derive it on the spot, which is the sum of roots and the product of roots that you have learned in your secondary school. So if I were to derive it on the spot, I am going to let the quadratic equation that is currently given, which is z2 plus alpha z plus beta, to be equal to the factorized form. And we know that the roots are z1 and z2. So this is going to be this is going to be equal to z minus away the root, which is z1, then z minus another root, which is z2. And if I were to expand this, we will be getting a z squared minus z1 plus z2 z plus z1 times z2. Z squared minus sum of roots z plus product of roots. If you were to expand this, you're going to be getting exactly the same result. So if I were to be doing the comparison, we can see alpha is going to be equal to minus of this. So therefore, we can see that alpha is minus of z1 plus z2. It is not asked here, but I guess in the last part we will be using it, so I'm going to just quote it. Beta is going to be z1 times z2. So based on this, can we now try to think whether it is necessary for alpha to be real? So alpha is equal to z1 plus z2. From the previous part we have analyzed, z1 plus z2 can be either having an argument of pi over 2 or an argument of 0. So if z1 and z2 happen to be one where the argument is equal to 0, then z1 plus z2 happen to be a real number. But like what we have discussed, since it is also possible for the argument of z1 plus z2 to be pi over 2, which is going to be a point that is representing z1 plus z2 on the imaginary axis, so it is going to be a complex number. Okay, so this is going to be producing for me a complex number, this version. So yep, I guess alpha is not necessarily going to be a real number. So my conclusion is, since the argument of z1 plus z2 can be pi over 2, so therefore z1 plus z2 can be complex number. Therefore alpha, the question says, is it necessary for alpha to be a real number? Alpha may not necessarily be a real number. Okay, this is for part C. Let's take a look at part D. Given that alpha is not real, and we want to also make sure that the modulus of z1 is equal to the modulus of z2 is equal to square root of 26 over 2. We want to find the values of alpha and beta. So if alpha is not real, that means we will need to go for this scenario. Alpha is not real. Okay, for this scenario, alpha is going to be real because z1 plus z2 is going to be a real number since the argument is going to be equal to 0, which means that we are going to be going for point B to represent Z2 for our scenario here. Okay, so for part D, since alpha is not real, so Z1 will be represented by this point and Z2 will be represented by point B. And we want to make use of the information that is given to find the values of alpha and beta. Alpha is going to be minus Z1 plus Z2, beta is going to be Z1 times Z2. So we want to find the actual values of Z1 and Z2. And to do that, I am going to make use of, again, what Z originally was represented by. So the format that Z was represented by here. Okay, so I'm going to make use of Z again. Let me erase these two. So what we have now is, for this, the question says, if the modulus of Z1 is equal to the modulus of Z2 is equal to square root of 26 over 2, we are going to, for part D, let modulus of Z be equal to square root of 26 over 2. And the modulus of Z is going to be equal to, if I were to make use of this, square root of 2 cosine t square plus 3 sine t square. This is equal to square root of 26 over 2. Squaring both sides and doing some quick evaluation of this, we have a 4 cosine square t plus 9 sine square t. This is going to be equal to 26 over 4. I'm going to multiply this by 4 throughout so I can not work with a denominator here. So this will become 16, but we are going to be solving this trigonometric equation. So I want all to be in terms of either cosine or sine. Let me just go for sine. So this will be 1 minus sine square t. And plus 4 times this is going to be 36. Then sine square t, this is equal to 26. So we have a minus 16 sine square plus 36 sine square. This gives us a 20 sine square t. And 16, if I were to bring it over, 26 minus 16, this gives me 10, which means that sine square t is going to be equal to 10 over 20. It is going to be 1 over 2, which means that sine t is going to be equal to plus or minus 1 over square root of 2. But the thing is, we are working on A, B. A representing Z1, which is one of the Z, and B representing Z2, which is also one of the Z. So for both of these cases, sine, which we are working on now, is going to be representing the y coordinates of the 2 points. So it must be positive. Okay, that is why between plus minus, we are going to choose the positive 1 over square root of 2, and this is because we need 3 sine t, which is the y coordinates of both Z1 and Z2, to be bigger than 0 in order for us to fulfill the requirement that alpha is going to be a complex number. Okay, so we have this. Sine is equal to this, which means that t is going to be equal to pi over 4. This will be meant for A, because when t is equal to pi over 4, we have a positive x coordinates for point A. Or the other possibility will be 3 pi over 4. If I were to solve this, this is going to be for point B, because cosine 3 pi over 4 is going to be negative. So based on this, we can now work out Z1 and Z2. Then we can put it into here to find alpha. We can then put it into here to find beta. Let me use this space here to find Z1, Z2. So Z1 is going to be equal to 2 cosine, here, Z1 is going to be here, pi over 4 plus I, 3 sine pi over 4. So this is going to be equal to, here will be 1 over square root of 2. So we have a 2 over square root of 2, then plus I. This is also 1 over square root of 2, so this will be 3 over square root of 2. This is Z1. As for Z2 is going to be us using t to be equal to 3 pi over 4, because we want the x coordinate of Z2 to be in the second quadrant, negative number. So cosine 3 pi over 4 is the one that's going to be giving me a negative So this will be 2 cosine 3 pi over 4 plus I 3 sine 3 pi over 4. So this is going to be this cosine 3 pi over 4 negative 1 over square root of 2. So minus 2 times of minus 2 times of 1 over square root of 2. So it will be this. Then plus I, this will be 3 times of 1 over square root of 2. So 3 over square root of 2. So now we have Z1, we have Z2. We are going to be making use of this to find the value of alpha. Let me erase this. So if I were to now make use of this Z1 and Z2, and if I were to find alpha, alpha here is going to be equal to, alpha here is going to be minus Z1 plus Z2. Okay, this will be minus, Z1 is going to be this, 2 over square root of 2 plus I 3 over square root of 2. Plus Z2, Z2 is this, minus 2 over square root of 2 plus I 3 over square root of 2. So I guess this and this can be cancelled. So we will have this times this multiplied by a minus, sorry, this plus this multiplied by a minus, we have a minus 6, minus I 6 over square root of 2. This is going to be alpha. As for beta, beta here is going to be Z1 times Z2. So it is going to be, Z1 is this, 2 over square root of 2 plus I 3 over square root of 2 multiplied by minus 2 over square root of 2 plus I 3 over square root of 2. We can definitely just do the expansion as per normal, or we can also see this as a plus b, a minus b scenario. If I can just rewrite this as the a plus b, a minus b scenario, we can probably write it as like that. I 3 over square root of 2 plus 2 over square root of 2. This will be the a plus b. Then if I were to just flip this, we have a I 3 over square root of 2 minus 2 over square root of 2. So this will be a I 3 over square root of 2 square minus away 2 over square root of 2 square. And if you were to be evaluating this, you will get the final answer here to be minus 13 over 2.